Okay, Nikita Nekrasov with kitchen systems.
Okay, so I would like to start by thanking the previous lecture for explaining that what we discussed yesterday was the Krichever genus. In fact, the generating function of the Krichever genus or of Krichever genera of the moduli spaces of rank n charge k instantons, which are mathematically torsion-free sheaves. So rank n torsion-free sheaves on P2, trivial over a fixed line at infinity, and so this was this is a function, or so this it takes values in whatever cohomology theory you prefer of a point, a covariant cohomology with respect to the group of changes of trivialization of the sheaf at infinity cross GL2, which acts on P2, preserving the line at infinity. And so I had parameters Q1 and Q2, which sort of live in the maximal torus of GL2. And K is the now this is somehow a change in notation. So this was Q3, which was e to the epsilon 3 in my lecture yesterday. And so this is a useful point of view, except that it sort of treats the parameters Q1, Q2, and Q3 in very different manner. So Q1 and Q2 are sort of very important because they rotate the space on which the sheaves live. And Q3 is just this strange parameter which you use to weight the exterior powers of the tangent bundle. So today we will remedy this and restore the democracy but of course, to go to the next level, you have to suffer a little bit, and sometimes it means, sorry for cultural references, you have to hang on the cross. So this is done by crossed instantons. So, but this is this is to be discussed. I want to continue the logic of the presentation. So the logic was the following: that the localization gives you a way to present this genera as sums over fixed points, and I without explanation, I just presented to you the fixed points as collections of partitions. And so this whole thing became just the partition function of some StatMech model, but we are not interested in partition function per se. We want to study correlation functions. And so the main question is, what are the good observables? And as you learned, as you have probably learned from the lecture by Stas Smirnov, there are two types of interesting observables. There are order operators and disorder operators. And so we will study the order and disorder operators for this model. Well, it depends. Yes. Order. Okay. Yes, yes. Over n Young diagram. Yeah. Yes.
Were you considering like process rank 2? And some sort of partition function looks like you're counting ideal for each Young diagram, but you're not considering that there could be a morphism from one rank function to the other.
I was, of course. Of course, yes, because they were talking to each other. In fact, somebody asked me, maybe Vanya asked me. So they had labels alpha and beta. So alpha was talking to beta. Oh, Senya asked. Sorry. It was a very important question. Okay, so order and disorder. Operators. Well, the word operator here doesn't mean much yet because I did not present this as a kind of Hamiltonian problem when you have some operators acting on some space of states, but it is also possible, and if you're interested in details, you can ask Professor Connor, who represents the same thing as a matrix element or maybe as a trace of some product of vertex operators for some multiply toroidal algebra. And so then everything indeed has interpretation in terms of operators, but here I'm talking about operators in kind of physical sense. They should really be called observables in the sense of probability theory, complexified probability theory. Okay, so what's the difference between order and disorder? Well, order is just something, order operators are something which can be defined kind of simply. Your original problem is some measure on some measurable set, maybe complexified measure, and your order operator is just a function on this measurable set. So something which you can easily define to be, whose expectation value you define simply as an integral against the measure. So, well, it turns out that there are kind of smarter ways of organizing these functions. So we want to have some way of assigning an interesting quantity to the collection of Young diagrams using essentially the characters which we presented last time. So let me first start by introducing the Y observable. So Y observable. And just anticipating Vanya's question, so the letter Y was invented for its own reasons, and but indeed there is some relation to the Y functions of the Y systems. And there will be also Q functions, which this is not a question. This is it's a name. No, the question why was in Smirnov's talk. So I'm only talking about how. Of course. We will be doing exactly that. The smart thing to do is to introduce order operators, disorder operators, stare at them. You have no idea what to do with them, but then you bring them together and then life starts. Just like in the book of creation, of course. Okay, so the observable carries a letter x. X is a part of observable. It's a parameter, but it is evaluated on my random variable, which is a collection of Young diagrams. And so what's the evaluation? Well, it's a product over this indices alpha from 1 to n, and then you need to remember this picture we had with blue and red boxes. And so let me specify that. Okay, so this is our. So this is so the content with index 1, 2 of a box, which is, remember, a collection I and j, is just epsilon 1 times I minus 1 plus epsilon 2 times j minus 1. And this is written for the cohomological theory and for the elliptic. You just put the theta function. So what is it? So it's a rational function. So this observable takes values in the rational functions of x. So valued in, well, rational or meromorphic, depending on, again, which of x for cohomological theory, or this would be degree n line bundles on elliptic curve in the elliptic theory. And so what it does, so it gives you a section of a degree n line bundle whose zeros tell you the positions of the boxes which can be added to the corresponding Young diagrams, and the poles give you the positions of the boxes which can be removed. So it's just a useful thing to have. And why is it useful? Well, if you expand it in rational case, if you expand it at infinity, it gives you the Chern characters of universal sheaf evaluated at a point. So it's why is what? No. Okay. No, not quite. No. It is a coincidence. It's how to say. It's an accidental fact for A1 type theories. Yeah, for A1. It's more complicated for other theories. No. Why of course is why of course is very important in describing Zabel-Putin curve, but it's a complicated object actually. So we'll I hope we'll get to the Zabel-Putin curve And so, so for the n equals to 2 star theory, the W, which you mentioned, which would be a point on the elliptic curve, would be the ratio of y over y of x plus the mass. So it's, y itself is a very complicated object, actually. Trigonometric. Well, but it's okay. So once you have this, it's kind of easy. Yeah. No, it's okay. So both rational and trigonometric cases are special in the sense that there is a special point where you can expand things, and on elliptic curve you lose this property. So it's you have to think, slightly differently globally, and you just have to think about the object in elliptic homology this thing represents, and I just said what it is. This is the universal sheaf localized to the point 0 inside C2, which is P2 minus P1 infinity. So it's a point which is fixed by the action of the torus, and this rank n sheaf, which so we have rank n sheaves which are parameterized by the modular space, and you take the universal sheaf over the product of the modular space and P2, and then you homologically, take the homological fiber over the point at 0, and so that gives you an object in elliptic homology of the modular space, which is represented by this y function. So of course there is just Andrew would have said the whole thing just in one word without any formulas, but I mean, I'm trying to present it as a stat-mech problem, so I have to write lots of formulas. Yes, Colin? No, just -1. I think so. Yeah, because it's so what this thing is, it's like the determinant of x minus matrix phi. If this were a finite dimensional matrix, so when you expand log of something minus, you get just a single -1. If you had plus, then it would be -1 to the alternating. Unfortunately, Sasha Veselov has left, and this is the matrix phi from his lecture. But matrix M from his lecture. Right. That's why it's in quote marks. That's why it's quote marks. Yeah. Well, this theory is not that pathological, actually. It's but it's just I mean, we can discuss that. It's just that the fact that once you go to 6 dimensions, the parameter x becomes the choice of light connection on torus, and there is no, well, there are special points maybe when it's trivial, but there is no analog of infinity, so to speak. So. Well, there are several. Well, the perturbative regime is when q goes to 0. So this is where so the whole thing just disappears. Okay, so this is this is observable, and it's kind of defined locally in terms of my random variables. So I give you lambdas, and we just compute this. So it's nothing terrible happens. The only thing which is kind of unpleasant is that it is a meromorphic function, so it has poles. And as I hinted here, this expression is meant to represent something like the Chern polynomial. So if E were a vector bundle, not a sheaf, this actually would have summed up to indeed a polynomial in X. And even in elliptic homology, it would have meant that you would have just a holomorphic section of some line bundle over E, not a meromorphic one. So it means that this, which kind of reflects the fact that it's not a good thing to restrict the sheaf at a point. It's not a very good object. So it turns out that there is a way to fix that problem. E to the epsilon 1, e to the epsilon 2. Yeah, I'm just, in Andrew's lecture, he was always using multiplicative notations, and I'm kind of used to additive notation. So so epsilon is for additive, q is for multiplicative, and the generating parameters they have a slash, so that we will not get confused. All right. Okay, so so what do I mean by remedying this problem? So let's suppose that I'm evaluating the expectation value of y. And for convenience, let me shift the argument of y by epsilon 1 and epsilon 2. So by definition, it means that I'm taking 1 over z, and then take the sum over all lambdas, the measure which we had yesterday, and then just evaluate y of x, y of evaluated at lambda 1. So, okay, so it will be some function. This depends on epsilon q. By the way, I'm not sure we know what does it mean to study 1 over Krichyver genus. Maybe, anyway. It might have some meaning. No, maybe it has a meaning. Okay, thank you. But you should be careful. In algebraic geometry, normalization means something completely different. So, okay, but let's just look at it. So this is my definition of expectation value. And let's just see where are the poles. So there are poles. So this expression has poles in X. So where are they? Well, let's. Yeah, because it cancels out. So the perturbative part is here and there, so it just cancels. For this purpose, it's mu. Check your notes from yesterday. Yes. Okay, so by this definition, so the poles come from. So the poles happen at points of the form A alpha plus some linear combination for some ij. Maybe I should write like n. So poles. And they come from the sum over all Young diagrams, all collections of Young diagrams for which from configurations where the inner boundary of lambda alpha contains the box ij. So in the ensemble of all Young diagrams, the ones in which the diagram associated with color alpha has the box ij in here, they will contribute to the poles of this expectation value. Okay. But now let's do the following. Let's remove ij from lambda alpha. Unfortunately, well, it would be great if we could just copy and paste. So that way, so this is where it was, this is where it was, this is where it was. So I performed a little bit of surgery. So I removed the red box. Sorry, it's not, okay. Let me draw it a little bit more carefully. And now it became the blue box. And two red boxes appeared. So let me call this lambda alpha tilde. So this is just saying, when I say that I'm removing, I'm just saying that to the collection of this type, I can associate another collection where at the place alpha, I replaced lambda alpha by lambda alpha tilde. And so, of course, the contribution of that diagram to these expectation values is something finite. It has no pole at this point. But now I want to point out that the evaluation of y of x now without a shift at this guy and when x is equal to what we had before, is equal to 0. So precisely because now this box became the blue box. And the blue boxes are in the numerator. And if there is no shift, then that's exactly where the 0 will be. So it means that there is a chance that if I add to this observable something proportional to inverse of y, then maybe the pole will cancel if we adjust the numerator properly. And the first thing which we should do is to introduce the instant on counting parameter q here, because the weight of that diagram, the size of that diagram is 1 less than the size of that diagram. So since we weight diagrams with the weight q to the size, we need to account for that. So there will be a q in front of it, so we can think of this as a small correction, because q is small. And then the whole question is what should we put in the numerator? And a little bit of computation shows that according to the rules of Critch-Verginus, more or less everything which is downstairs should be accompanied by the same thing upstairs shifted by epsilon 3. And then there is some symmetry here, which I guess should be epsilon. Maybe it should be minus epsilon 3. Okay, I will write a general formula now. I don't. Sorry, I apologize. I don't remember don't remember details of that type. And so, if you're not careful, you think that's the end of it. But it turns out there is a. Okay, what am I trying to say? Yeah. So now we've canceled the poles of this expression using the zeros of that expression, but the price we paid was that we had a numerator, and this has now new sets of poles, and those poles have positions which are shifted by epsilon 3 and epsilon 4, and that's the voice of the oppressed. So the epsilon 3 and epsilon 4, which we didn't use before, we didn't take them seriously, now they want to be taken seriously. And so we need to add more terms to cancel poles at A alpha plus epsilon 3 plus and also epsilon 4. And so begins a story where you kind of see proliferation of poles. You keep adding terms. They are multiplied by smaller and smaller coefficients. And then you cross your fingers, and then you end up writing the whole formula for the whole series, which happens to be convergent. And that's actually a fortunate thing which was not guaranteed. And we will maybe mention some generalizations of this model where this series only makes sense as a formal power series. All right, so now I want to write a formula. So what Andres, so okay, let's do it slowly. So there is a limit in the rational and trigonometric case where you can send epsilon 3 or epsilon 4 to infinity and q to 0 simultaneously. And that would kill some of those terms, and make it simpler, make it look simpler. But I want to present this formula, and then we'll do certain manipulation to the whole model, and we'll get to the models you want to discuss by other routes, so by the orbifold procedure. But it's true that, okay, maybe I should say that if in the original measure mu, instead of the numerator being exactly the denominator with arguments shifted by epsilon 3, my numerator was something else, like the content polynomial, then this procedure would have stopped at the second step. Numerator would be some polynomials or fixed holomorphic sections of a line bundle of appropriate degree, and so we would not have generated extra poles by adding this term. So there are simpler models which are limits of what we discussed. So the whole thing is now called the X observable. Actually it's chi. So this is and this observable is called the QQ character. And by I think it actually has a term already at this order. Right. So this tiny correction, which you would not have observed if epsilon 1 or epsilon 2 was equal to 0, this is what makes this. It opens the window into the whole new world, actually. So this is a very important, easily overlooked overlooked factor. So this Q character is a generalization of Q characters introduced by Frenkel and Reshetikhin. And the reason it's called QQ is not because of the one flew over the QQ nest, but because of the Q1 and Q2 parameters in this equivariant K theory. So these are for equivariant parameters. I mean, maybe we should call Q1, Q2. All right, so let me write the formula again. Apologize. So this is. So the formula is the following. So chi of x is a sum over a single Young diagram. So this is actually should be called the fundamental. So there is Q to the power the size of Young diagram. So you should think of these terms. So this corresponds to the empty diagram, and this corresponds to the single box Young diagram. And then we, yes? Yes. Yes.
Remove that monomial from your Young diagram, and then you do this modification here. Is there a way to describe it with respect to pointing counts on C2 minus a point or something?
No, but you cannot remove a point because the rest of the ideal is there. If you remove the point, you.
It's like you have your first point is on origin, but you're kind of making it less fat, right? By removing that monomial part.
Right.
Okay. So I want to understand with respect to this modification, this thing on the left blackboard, and I think of it as something. What is this partition function called?
Very good, very good question. That's oh, I erased. I already wrote it. It was a partition function of crossed instantons. No, okay, I'm joking. No, I wrote it, but I didn't explain what it is. No, we're guessing there. We're guessing there by meditating on the formula. So we need the formula, and then we'll understand where it comes from. No, I did not. Okay, times. So the ingredients are familiar to you by now, but the coefficients are now different. So now what are we doing with them? So this is x plus epsilon 2 plus the 3, 4 content. And this is x plus. So I should, again, use the colored chalk to make it more accessible. So now I'm using another version of the content where the content of the box is measured using epsilon 3 and epsilon 4. So what do you see here? So, okay, so this is some expression built out of the y functions. It is built according to the shape of the Young diagram we are summing over. So we use the contents of the boxes of that Young diagram to shift the arguments of the y absorbable, which was the absorbable on the ensemble of n Young diagrams, those guys. And then there is a prefactor, which is precisely the prefactor of Krishver genus of the Hilbert scheme of points of k points where k is the size of this diagram on C2. But now the z parameter is e to the epsilon 1, so it's q1. And it is equivariant with respect to the torus, which acts on this guy with weights q3 and q4. So this whole thing is really just a push forward in the K theory, in the elliptic homology of K theory of the Hilbert scheme of points on C2, but this is not the C2 on which our original instantons were living. And so it's a C2 on which the torus, some torus, acts with weights Q3 and Q4. Okay. So while you were gone, I changed the argument of Khrushchev-Arjunas. Okay. And so now we are kind of trying to make lines sleep with lamps, because so the roles of, so the guys who were just kind of silent observers for the original problem, this epsilon 3, which was just sitting in the numerator, wasn't doing much, now became quite important, because now they're all over the denominator of this localization formula. But okay, but you can ask, why bother? Why all this trouble? Well, it's worth doing that because the main theorem says that the theorem, which is elementary in this case, says that the expectation value of this observable is holomorphic in X. So all poles have been cancelled. So in fact, it means that you can write it as a product over alpha from 1 to n of theta function x minus capital A alpha, where capital A alpha are some line bundles on the elliptic curve which encompass all the information, well, not all information, but they encompass the information about the, so they depend on Q. So capital A alpha depend on Q. We know that has exactly n zeros because, and I should have stressed that more, so the Y observable was degree n line bundle on X. Because there is always one blue box more than red boxes, and I had n factors. So Y is, and you can check that in my definition that these are good line bundles. And so this is degree n line bundle. So this is degree n squared, 2n minus n. So it's degree n, and so on and so forth. And so again, because there are also one number of blue boxes here is also one higher than the number of red boxes, the degree of the line bundle is always, all terms contribute to the same degree. Yes? Yes? Sorry, that's not what I'm, yeah. Ah, okay, so you want to, okay, so. Are you talking about packaging n partitions into one big partition? Yes, yes. Okay, so it's like then there's something like that. Sorry, my drawing is this. Okay. I mean, we could. Okay. Are you asking whether there are relations where you add and remove not just boxes but partitions? Yes. No, but you see, we're getting the Paul constellation in the sum over n tuples by a single sum over a single Young diagram here. It's one diagram takes care of all. Okay. All right. So as Artan was asking, what the hell is this formula? What is this formula for? So if the original partition function was just this normalization constant was just a push forward of 1 in the appropriate in Krichyver genus, it's okay, not 1. It's a push forward of the exterior tangent bundle, exterior algebra of a tangent bundle over the modular space of torsion-free sheaves. What is this formula? To understand what this formula is, it's actually better to reformulate the definition of Krichyver genus as a push forward of 1, not as a push forward of the exterior algebra of the cotangent bundle, as a push forward of 1 for the abstracted manifold. So if you take the modular space of torsion-free sheaves, but view it as a accidentally sitting as a zero section in its cotangent bundle, and in reality, you want to have a kind of a generic section of this cotangent bundle, so you just want to have some points. So there is some, if we were on a conference on symplectic geometry, when everything is flexible and complex structures are not integrable, we would have deformed everything and just we were counting points. But luckily here we are in a covariant rigid situation, and so we're not allowed to count points as points. We should compute covariant integrals. But the message here is that there is a zero-dimensional space, zero-dimensional virtual cycle, which is represented by an integral of 1 over the cycle is represented by Krichyver genus. So now we're going to generalize. We just generalize this problem and make it look like a problem which now describes something like sheaves which live now on the cross, the promised cross. But it's a cross in like in quaternionic sense. So it's a cross of two complex planes which are transverse. And so there is one plane where we study rank n sheaves. And then somehow we bring a tunnel microscope. We bring just one. We have a transverse plane, transverse inside the ambient four-dimensional space. And somehow there is a problem of simultaneous counting of rank n sheaves on the horizontal plane and rank 1 sheaves on the vertical plane, and these sheaves talk to each other. So what I'm drawing here is the picture from string theory with strings, open strings connected to stacks of branes. But somehow so this factor is precisely the mu measure. It's a usual mu measure for a single Young diagram, except that now the parameters are epsilon 3 and epsilon 4. So this is just a factor responsible for the ordinary integration of a Hilbert scheme of points on C2, and this is C2 with coordinates 3 and 4, which explains why we have coordinate weights 3 and 4. And that measure here is the measure for integration over the modular space of rank n sheaves over the horizontal C2. And then there are some cross factors, so somehow having to do with sheaves talking to each other. And these cross factors are these ratios of y functions. And if you go back to the definition of y function, we can make it look much more symmetric. And so partially restore the democracy. So the vertical guy is U1. Vertical guy is the U1 gauge theory. And it's a U1 gauge theory which interacts with UN gauge theory. And so if you integrate out the degrees of freedom on this U1 gauge of this U1 gauge theory, you get an observable in UN gauge theory. And that's this observable chi. So yes. So the eigenvalues of transfer matrices are Q characters. These are QQ characters. These are quantum objects. If one of the Q parameters goes to 1, they become Q characters. And they become eigenvalues of transfer matrix. Of a transfer.
Are these things also eigenvalues? Do we describe eigenvalues?
Ask Professor Kono. So these are, I'm told by different people, including Professor Kono, that you can describe them using toroidal algebras. So you go so Q characters is what you get for quantum affine, quantum loop, right? And you need to go to toroidal. And well, actually these guys, in the K-theoretic case, Peston and Kimura showed that these guys just generate what you call the QTW algebra. It's W algebra, so they are not quite commuting. So you don't want to view them as eigenvalues, but they're as close to commuting operators or eigenvalues as they could be.
So they form some kind of vertex.
From W algebra. What do you call it? QT. Now they should be called QQW algebra because Q1 and Q2 are on equal footing. Historically, people had Q parameter and then T parameter, and they were kind of awkward. The relation was kind of awkward. But it should be just Q1 and Q2, and they're completely symmetric. QQW algebra, yes.
So this ratio of the two y functions is some contributions of arms between rank 1, or 1,
So these guys, the numerator and denominator, the meaning of is the following, that you can try to deform a sheaf in here by removing a box. I mean, removing a box means going to the ideal of lower codimension or high dimension and moving it all down over here. So they want to, they deform by each other. So this guy deforms to here and this guy deforms to here. So they, when you open up the definition, you will have 4 types of terms. One plus interacts with plus, minus with minus, plus minus.
What I'm asking is like if I wanted to reformulate this as count of rank n plus 1 plus C4, and there is a component where this thing sits in the exact sequence between rank 1 and rank n, and then I can look at automorphism of that exact sequence. And then there is a
right. Yes. So in fact, the way this formula can be understood is by, well, the way I understand this formula is using non-commutative geometry, but it probably is equivalent. So I reformulate the whole thing as a story living on C4. And so you have a huge, so the sheaves which are supported on C2, they are, when you present them as cohomology of essentially Koszul complex in the transverse direction. And so you have one guy from here, one guy from here, and then you just compute the Holmes or X. So that's all there is. I don't know whether this can be understood in 2-dimensional terms because it's a singular surface. But that's basically it. And there is a kind of finite dimensional model for this moduli space of crossed instantons, from which this can be derived by usual integration. Okay, so that's all I want to say for the moment about the order operator. And now I want to introduce disorder operator. Why is this? It's because it's a function of lambdas. Complicated, but it's explicit function of lambdas. I'm not modifying lambdas. So disorder operator is when you give an instruction to the path integral so that it's being computed over some kind of single configurations, or it's configurations which are modified maybe in some non-local way. Yes. That's the democracy in the. Okay, that's full. Of course. So, I mean, there is a formula for. So there is rank n here, rank m here. Here we had the parameters a1, an. Here we'll have the parameters b1, bm, and x is kind of relative. It's a distance between the centers of mass of a's and b's, and so this you think of them as of evaluation parameters for the fundamental representations of the Yangian, or some kind of Yangian. Okay. So I could write the formula, but maybe we will not learn much more from. It's just a generalization of this formula. Yes. What k? Where do you see it appearing? Sorry. Why do you need to see the instant number k? Well, because I gave you the formula for k. No, the message here is that the instanton number is shared between blue and red. So Democrats and Republicans have the same pot of money to deal with. And they just go from one to another. That's this whole story. So from cancelling poles to other poles. All right. So okay, if like, so there is a slightly redundant there is a redundancy which changes the. So we can normalize, for example, I can normalize A's. So the center of mass is equal to 0. B's, the center of mass is 0. And then you have one degree of freedom left, which is so um cross un over u1, which is diagonal. This still has a center. So the center of that is u1, which is where x belongs. So the meaning of the parameter x, the spectral parameter of the transform matrix or the Q operator or also the Q character is it is also a kind of framing equivariant parameter, but it's a framing which you will not see unless you have two orthogonal stacks of branes. You see, when we study shifts on P2, and we say that the framing group is GLN, it's not quite true. The framing group is PGLN. is GLN modulo the center. Now, if I do two stacks, and so then the kind of a framing group will be GLM cross GLN modular C star. And now one C star appears. And that's why X becomes, that's how X comes alive. Okay, so disorder operators are also known as surface defects. And there are many of them, and these are obtained by a procedure which also comes in several flavors. So maybe I will explain for befolding. But let me explain first of all what is it that I'm trying to do in maybe geometrically. So geometrically, we were studying sheaves on P2, which were trivial on line at infinity, and so that was related to doing gauge theory, maybe UN gauge theory on R4, which is C2, which is P2 minus this line. Now, in gauge theory, so gauge theory means there is some kind of path integral over gauge fields, some Young-Mills section. Now, in gauge theory, you can study observables also. So this is also meant to be a kind of limit of static mechanical problem. And typical observables which people study in gauge theory are the holonomies of Wilson lines, Wilson loops. So you take a contour. So this is the real contour. You take a holonomy. You take its trace and some representation, and then you study the averages. These are quite respectable things to do, and people on largest QCD study them on supercomputers. Unfortunately, in our world, when everything is formulated in terms of holomorphic bundles or sheaves, we don't have access to those observables. Now, fortunately, if you do knot invariance using Chern-Simons theory, you know that in three-dimensional, so in 3 dimensions, such observable can also be understood as a disorder operator, because in Chern-Simons theory, having a knot or a link, okay, we need to ask Vanya to draw us a picture of a knot. So if I have an observable like that associated with some contour, the gauge field over which we perform the path integral has a singularity. And the singularity is such that the curvature of the gauge field now has a delta function source support on this curve. And the actual magnitude of the curvature singularity is related to the representation which we evaluate Wilson line. So we can generalize that aspect of the Wilson line to 4 dimensions and define the observables which will be codimension 2 defects. Now, in the language, so these codimension 2 defects can be defined in many, many ways. One of them, so in the language of algebraic geometry, if you have a complex surface and now C is complex curve, and I was interested in studying sheaves over S, I can now impose the condition that the restriction of my sheaf on the curve comes with the flag of subsheaves. And I could define a new moduli space which parameterizes not just the sheaves on the whole surface, but the flags of subsheaves of the restriction of the sheaf on the curve. And we can also do it in a more homological sense that if your curve, for example, is defined by some equation locally, so suppose the curve is defined by the equation z2 equals to 0, equation of C, then we can study the flag of subsheaves of my sheaf defined globally, requiring that they fit into the sequence where the last term is the sheaf of multiplied by the equation. So the sections of that sheaf are the ones which are divisible by z2. So they have to vanish on this curve. And so that's morally the story which we're going to follow. So this is analogous to the well-studied problem in the in the world of holomorphic bundles on curves, where you fix a parabolic structure at points. So just think of curves as divisors, so you now fix a parabolic structure at divisors. So that can be defined in any condition. E is torsion free on S. Okay, so now there's no I did not talk about, I didn't say word Hilbert scheme. Where did you get it? Okay, it was. Okay. No. We have the modular space of sheaves. Okay, if the sheaves were of rank 1 and S were P2, there would be a Hilbert scheme of points on C2, and then we'll be studying. I forgot what it's called. This condition tells you what type of singularity the curvature has. So it's the eigenvalues of this matrix J, which multiplies. So now it's a two-dimensional delta. It's a two-dimensional delta function which is supported on this curve C, and the eigenvalues of J tell you that there is a flag of subspaces. So this is a non-abelian gauge field. It's a non-abelian curvature, but close to the. So this is a transverse picture. This is my curve C. And so this is some. So locally, I'm kind of embedding a bunch of abelian vortices into the non-abelian gauge group. And so how I embed is determined by this matrix J. But now you can order your vortices by the strength, and so that tells you what is the flag of subspaces. So this is the delta function of Z2 bar. So this is Z2 plane. It doesn't have to be Z2, it's just that, again, traditionally we place the surface defect at along Z1 plane. Okay, so it turns out there is a very convenient construction which realizes this parabolic structure via kind of an orbifold story. And so, so imagine that we were doing gauge theory not on Z1, Z2 plane, but on Z1, Z2 tilde plane. Where Z2 tilde to the n is equal to z2. This n happens to coincide with the rank of gauge group. It doesn't have to, but for my applications, it will be. So I'm using that. So imagine that I'm doing something simple on the covering space, z1, z2 tilde, but then I try to project. I project on z1, z2 plane. So project. Now, as a complex manifold, the quotient of C, so I'm doing like quotient of C cross C by Zn.
This is just part of the list of length spaces N1.
There is no length space yet, and there will not be in this part of the talk because I'm quotienting C by Zn, not C cross C by Zn, just C. And I'm using the fact that unlike C cross C, C mod Zn is just C. And that's the proof. But there is something happens at the origin. So of course, if you just think about what I did some kind of cone. I took the space, I cut out big cone, and then I identified the point. So there is something happens at the origin, some kind of defect. So let me now give you the definition, which is rigorous, and then you can see whether it is illustrated by those pictures. So the definition is the following. We now define new measure on the same set, on the set of n tuples. So I'm taking this, so it's the same set, but I'm now defining a new measure, which is more refined. And it is refined in the following sense. In addition to the characters with respect to the torus with parameters q1, q2, q3, we will now keep track of the representation content of the cyclic group Zn. And so this group gamma, we should think of this group gamma as acting in a four-dimensional space C4 by rotating Z2 and Z4 coordinates in opposite directions. So it's part of the Calabi-Yau 4 structure. So there is Z4 tilde, and so the action is Z1, Z2 tilde, Z3, Z4 tilde goes to where omega are roots of unity. So this is the gamma action. In addition, and that's the tricky thing, which is, so in addition, this group gamma acts in the framing space. So what it means that the n-dimensional vector space C to the n, which is the fiber of my torsion-free shifts at infinity, the space n, so I'm taking it to be the regular representation of gamma. So that way, this has to do with the fact that I'm taking the maximal flag of subshifts. So if you choose other representations, and if gamma is not of this, then it would correspond to more general flux, which I don't want to study here. So different eigenvalues and right, precisely. No, because in my description I don't see this matrix. My description is not in terms of solving I'm not solving equations, Newtonian equations with its singularity. I'm doing something else. I'm just saying that I'm doing an algebraic geometric construction which is meant to correspond to a differential geometric construction involving those delta functions. That's the thing. You see, we are doing gauge theory here. So for us, this doesn't seem to, I mean, we don't see those directions. But we will see them when we will write the formulas for QQ characters. So that's something to keep in mind. Okay, so now the rule is the following. So we now assign I mean, I want to assign some quantity, some quality actually, to the parameters A alpha, epsilon 1, epsilon 2, epsilon 3, epsilon 4. And I don't want to call it color because I already said that we had n colors. I don't want to call it n-ality because it's a kind of an ugly word. So I just call it brackets of a letter. And so let's call this, so we call it C of alpha. So these guys, these things are valued they're valued in the n, which is not the group, but it's a group. It's a group of representations, of irreducible representations of my group gamma, which happens to coincide with the n, but it's kind of an accident. So C, and so for the regular representation, the function C should be a one-to-one, kind of one-to-one correspondence between the sets of between set 1 to n and the sets of irreps of gamma. And so let me label irreps of gamma by integers from 0 to n minus 1. And so R index gamma, it's a representation in which the generator omega acts by multiplication by e to the 2 pi square root of minus 1 omega over n. So this is the definition of R omega. And so C is some way of coloring assigning to my colors, which were originally numbers for 1 to n, an additional label. And if you like, we can just take C alpha to be alpha minus 1, one possible coloring. Now, 0 means trivial representation. So R0 is a trivial representation. So epsilon 2 is assigned 1, and that's meant to represent this fact. Epsilon 3 is 0, and epsilon 4 is minus 1. And now the definition of the measure is simply so new measure of lambda 1, lambda n is the product over the same I don't know, alpha beta boxes, the same set we had before, but now we only keep those terms for which the combined quality of the expression. So if I write it generically as a linear combination n alpha a alpha plus k1 epsilon 1 plus k2 epsilon 2 plus k3 epsilon 3. So we only keep those factors in this product for which the sum n alpha times c alpha plus k2 is equal to 0 modulo n. So I'm doing less work. I had a complicated formula which was a product. It was a bunch of factors being theta functions in numerator and denominator. I'm just crossing those terms which don't obey this selection rule. And the same set of Young diagrams. Young diagrams the same. The measure is new. And one more addition, which makes it more interesting, is that now I have more instanton weights. So these instanton weights have to do with the fact that my parabolic sheaves had topology along the curve, and so to keep track of all the first-chain classes of the quotient sheaves, I have new numbers, and so I have new fugacities. So what are these k omegas? So k omega is the number, it's a sum over alpha from 1 to n. It's the number of boxes in the Young diagram lambda alpha such that c alpha plus j minus 1 is equal to omega modulo n. So literally what I'm doing, I'm coloring my Young diagrams in n colors. I'm coloring them vertically. So for example, so this is alpha equals to 1, alpha equals to 5, let's say, and alpha equals to n. So the color of the first column of the first diagram, this is color 0. And so the next, so this is 1. And then if I have a column number n plus 1, in the first diagram it will also have color 1, 2n plus 1, and so on. Now, on diagram number 5, the color 0 will start at the column number 5. And then, yes?
Here you have extra condition that if such is need to be sitting inside each other.
Yes. We'll get there. I did not explain to you how to reconstruct the original sheaf from this collection of Young diagrams. These Young diagrams enumerate the fixed points on the new modular space. So it just. But as I promised, this should be a disorder operator. It should be an observable. So there should be a way of saying that this whole thing is associated to a configuration we start with. And so now I will apologize to Vanya and explain that this n-tuple of Young diagrams is not the n-tuple of Young diagrams over which we are sitting on the modular space of torsion-free sheaves. So So there is a map. And this is, I mean, for combinatorists. So there's a map from the collection, from the set of n-tuples of Young diagrams to the set of n-tuples of Young diagrams. So this is kind of a projection. It's a projection which corresponds to the projection from the modular space of parabolic sheaves to the modular space of sheaves. So forgetting about the parabolic structure. And so what is this map? This map, I don't want to make a silly mistake. I want to make a smart mistake. The map is the following, that the dual, so the jth part of the dual partition to the partition capital lambda alpha is equal to the alpha plus n times j minus 1th part of the partition lambda alpha. So this is the map. So the claim is that this crazy measure, which is obtained by crossing out lots of terms, when you sum over, so you sum over, call this map pi. Pi inverse of lambda 1, lambda n, of mu is equal to the old measure evaluated on these capital lambdas times an observable. And the observable can be understood as a, well, sum or integral over the space of parabolic sheaves, parabolic structures on a given sheaf. On a given sheaf associated with these things, it's essentially, again, the integral of 1, but now it's weighted with this with these weights where k's are related to the first-chain classes of the quotient sheaves. So the Q, the old Q is the product. So here we very good. So there is of course capital Q to the size of these big partitions, and then there is a it is better to reorganize the sum in terms of the variables Q omega defined in this way, where Z maybe minus 1, where Z omega plus n is equal to Q Z omega. And that's the beginning of the elliptic curve. So you see that you have a collection of particles, which, so you have an infinite collection of particles, but if you translate label of a particle by n, you just get another copy of that particle on the same elliptic curve, if you mod out by multiplication by capital Q. And so this thing becomes actually precisely Z omega times the first chain class of the associated quotients. But this is, anyway, this is explicit. It's despite the appearances, it's an explicit formula, explicit combinatorial formula, and And now we can, so we just need to understand maybe how large are the fibers of this map. So this map, it's actually infinity to 1. So there is the preimage of each collection of partitions is an infinite set, but this set has an interesting structure, which again should remind you it has to do with maps with quasi maps to Flach variety. So let me just explain maybe a few simple things. So if I look at the formula for lambda 1, so if alpha equals to 1, well, when j equals to 1, then by this formula, this is equal to lambda 1 transposed. Okay, so if I know capital lambda, I know the first column of my little lambda partition. Now, if I look at the lambda 1, 2, this is, so by this formula, 2, sorry. So so it gives me the second row, second column. And so lambda 1, 2 transposed could be any integer number greater than or equal than this one. So that gives me one integer, freedom. If I go to lambda 1, 3, so that's so that will give me lambda 3, and so I have now two integers. Which are ordered. And so if I go all the way to lambda n, lambda transpose, that's lambda n. And so I have now n minus 1 integers. So, so there is some triangular structure, which is the beginning of Gelfand-Setlin table of numbers, which are actually degrees of quasi-maps of P1, P1 being the line with coordinate Z1, which are mapped, so quasi-maps to the cotangent to the complete Flach variety. So in order to understand why do you have this triangular table of numbers, you might want to use, one way to see that is to use the quiver variety representation of the cotangent to Flach variety. So it's a quotient of a vector space with respect to the product of unitary groups of raising rank, growing ranks. So that takes care of most of the fiber, but not all. There are also finite pieces having to do with the possibility of inserting columns between n successive steps. I'm out of time. Okay. All right. So I think at the exercise session we might we'll discuss the relation. So the relation to parabolic sheaves. And the main claim is that the partition function of that object, so the expectation value of this surface defect, this disorder operator, is a solution to Knizhnik-Zamolodchikov-Bernard equation, which is the non-stationary version of quantum elliptic Calogero-Moser equation. And so in here, all the eigenfunctions of elliptic Calogero-Moser Hamiltonian are contained. Okay.
Any quick questions?
Yes.
We just erased this what's called fundamental.
Fundamental QQ character, yes.
But I see that you have all QQ characters.
Yes, so when I said that I could have m, or m of them, so there is a there is a formula for the kind of product of m fundamental for the representation, which is a product, that's the product of m fundamental representations, and unlike q characters, which would be just a product of those expressions, these guys have non-trivial OPE. So the prefactors will now involve the same measure for the modular space of rank m torsion-free sheaves on C2. And so what Peston and Kimura did, they interpreted those prefactors through OPE of vertex operators. So you can compute them not by doing geometry, but by doing algebra. Which is the fusion procedure. Yes, it is the fusion procedure. So the Y operator, so I'm sorry, Artan, sorry. Y operator is a vertex operator. It's like exponential of a free field. That's in that language. And then, yes. So you see, I explained what happens when the curve in question is the Z1 curve. It is defined by the equation Z2 equals to 0. So I said that when I approach Z2 equals to 0 at one point on this curve, I see the delta function, the curvature has a delta function singularity with some j. But this j varies along the curve. So what does this j belongs to the orbit, to the coadjoint orbit. And so there is the part of the data is a holomorphic map of Z1 curve into this coadjoint orbit, which is a Flach variety, which is actually cotangent to the Flach variety. And so that's what we're counting. But we're not starting from that problem, which is hard. Why is the curve? So P1 is just a Z1 compactified by point infinity. Oh, absolutely, absolutely. Absolutely, just that, of course, we are bound here by the sacred equivariance. So, because we only deal with things which are invariant under the torus section.
Okay, I think remaining questions can be delegated towards exercises and discussions. Lunch.